record this lecture. So as we always do, so far we have covered so much during this course, and I hope you don't lose the perspective of this. So just like thinking about what we have done. First part of the course, we were using descriptive statistics. We were able to use graphs and some ways to visualize the information. So that's what we did in the first part. Then we enter in the territory of inferential statistics when we start looking at um, 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 confidence intervals. So remember, we were able to build confidence intervals for the mean, having large samples and small samples, also for the population proportion, and also for the variance and standard deviation of the population. So that was good. In many cases, those confidence intervals are very helpful. So I was reviewing some of the COVID-19 graphs. So and many of them include some degree of uh, like an interval between. So we used well. So I want also, before I forget, because this is very important. So here, I don't know if you remember that we use the moving average. So the moving average, we use 5 observations, we take the average, and we move the observations down. So as you can see with the COVID data, I have seen it in many cases. Like, for example, if you make these like smaller periods, so you can see that the data fluctuates a lot. So in order to avoid this fluctuation and have a better picture of the disease, so they are taking a 7-day average. So most of the graphs that show COVID are based in a 7-day average, which is the same as the moving average that we mentioned before. So because in this case, I guess it's testing. So testing was going up and down. Today they have 100, yesterday 95, then 120. So the number were going up and down. So in order to make sense of this data, so they build this 7-day average. So I was trying to find some confidence intervals, confidence intervals, which are in many cases, we have, like for example, this is an example of a confidence interval. So we have COVID analysis, and we have the observed data, but also we have data that, um, um, for example, this is the real data, and this is the confidence interval. At some point, they are kind of like predicting what might happen with this. So we have a maximum possible, a minimum possible. So that's how it looks in real life. So in many cases, confidence intervals are extremely useful. And in many cases, we all have this kind of software that can help us make sense of the data. So we went through the confidence intervals, then we start with hypothesis testing with one sample. So we make a claim, and we use a sample to see whether or not that claim was true or not. So now we have 2 samples, and in these 2 samples, we have cases where the data comes from independent samples. So in these 2 independent samples, so we are able to measure the difference of the means. So we are assuming that there is no difference in the population, but then we in reality, we pull 2 different samples from 2 different populations, and we obtain different results. So that results are going to be used to compare the population parameters. So in this case, so we went through the 2 samples with for large samples, the 2 samples for small samples, assuming that both were independent samples. Remember, with the small samples, we have two different cases. We have the case of when the variances are equal, and then when the variances are not equal. So in the first case, in these two cases, we are using the t-distribution. And then we moved on a little bit more, and we analyze this case where we have the pre and the post. So that is also very important. In many cases, you might be wondering how things are improving or not. So you know that Lipitor, for example, I mentioned that before, is a good medication. You want to prove it. So and you take a sample and take the pre and the post and measure whether or not your hypothesis in this case. So if, for example, in the case of the jump, they jump lower. Now with the new choose, they are jumping higher. Or in the case of Lipitor, they have high cholesterol, so then they have low cholesterol because of the medication. So in this case, so it's also based on a sample that is dependent. So we have a pre and a post. Here is an old and a new. So we can make comparisons and see whether or not this is these two numbers are different from the expected. So so in this case, so in all cases, our standardized test, either the C-test or the T-test, are going to be based on subtracting the observed difference minus the hypothesized difference. Remember, we don't need this. We always do the observed difference divided by the standard error. So in all the cases, and we have to be very careful what we are doing, because all these cases are going to be the standardized test statistic is always going to be based on that approach. Look at the difference divided by the degree of variation. So we are going to have the standardized test statistic. So we compare this standardized test statistic with the critical value, and we decide whether or not reject or fail to reject. Okay, so that's what we did in the previous cases. In this particular exercise, we have two samples that are dependent. So it's the pre and the post. Okay, so the procedure is a little bit complicated. I hope you can make sense of the Excel file. And if not, and if you decide to do this by hand, so make sure that you understand the formula. For example, in this case, this is the summatory of all the differences squared. So we take the difference, we square them, and then we sum all of them. Here is the summatory of all the differences, and then we square that number, right? So this formula is a little bit not complicated, but has so many layers. So that's the reason I always like to use Excel. But anyways, so today we are going to be covering something similar of what we have been doing. So we are going to also test the difference between proportions. So we are going to have two population proportions. We are going to select two samples. So we are going to run our testing, and we are going to make sure that this test is going to, we are testing the difference between these two proportions. So use to test the difference between two population proportions. So we're going to choose two samples, two sample proportions. So there are three conditions. Once again, randomly selected. We always assume that this is very important. We need the sample to be randomly selected in order to avoid spurious results, meaning biased results. So samples in this case have to be independent, so we can have different sample size as long as they are independent. And the sample must be larger than large enough to use a normal sampling distribution. So if we have a very small sample, we have to do this like, so we have to make sure that the sample size of the the sample size of the first sample multiplied by the proportion, population proportion is greater than 5 in all these cases. This is for this is the probability of success. This is probability of failure for the first sample. So we need to know that all these cases are going to be greater than 5, right? So the greater, the bigger the sample, we don't have to be very, how to say, we don't have to care too much for that. So when the sample is big enough, of course, we always obtain numbers that are greater than 5. So, but when we have a small sample, we have to make sure that we have to test all these values, the sample size times the probability of success, the population proportion, and this is the probability of success, this is the probability of failure in the population. So if that numbers, if those numbers yield values greater than 5, so we don't have any problem, so we continue with our analysis. So this is a little bit labor intensive. It doesn't mean that it's difficult. It means that we have to do a little bit more of work. And I can assure you that, I mean, this Excel sheet that I found online, I can tell you I didn't do it. I think I put the reference over there. It's very simple. So it tells you exactly what you want to know, and it even gives you the values that you need to compute. So 2Sample C-test for the difference between proportions. So remember, in previous cases, when we are using proportions, we are using the C-test. So if these conditions are met, then the sampling distribution of the difference of the sample proportions is a normal distribution. So so this follows a normal distribution. So the mean is going to be the mean of the sampling distribution. In this case, for the sample proportions, is going to be equal to the difference of the population of the two different populations. So so once again, we are using our theorems to make our life easier. So and once again, so so we are assuming that these samples are large enough, and that large enough is confirmed by using this test. Okay, so that original test has to be met in order to be able to find or to use the C-test. If any of these numbers is less than 5, we are not able to use the C-test. Okay, so make sure that your sample, so you can multiply the sample size times the probability of success in the population proportion, and this is the probability of failure in the population proportion, and is multiplied by the sample size of the first. So we do the same with the two. So I cannot emphasize this too much because it's very important that we make sure that those values are greater than 5. So let me, I was watching my favorite show before this. Let me stop it, okay? So, so basically, we need to do a lot of work. So first of all, in order to find the p bar, which is going to be a weighted estimate. So in order to solve the standard error, we need to find a weighted estimate for P1 and P2. So so in this case, so we have to use these proportions. So we are going to use this weighted estimate of P. So so we are gonna do so x1 is gonna be n1 times p1, right? So the sample proportion times the sample the sample size times the sample proportion of the first one, and then x2 is gonna be the sample size of the second sample times the sample proportion of the second sample, right? Sounds like a tongue twister. So in order to find this x, first we have to solve this, and then we are gonna divide by the summatory of the two different samples. So that these values are gonna be helpful because I need the weighted estimate of P1 and P2. So also I know that when I get this number, if I subtract 1 minus P bar, I'm gonna get Q bar. So I'm gonna have P bar, Q bar, and that is gonna be multiplied by the reciprocal of the sample sizes in each sample. So we are gonna add them up, then multiply by this, right? And then take the square root. So as I said, this formula seems to be a little bit more elaborated. You can do it by hand, which you are welcome to do it. But we have a very easy way to solve this case. So we have the standard error. So this standard error, remember, we're going to look at the difference of the observed differences divided by the degree of variation. So in this case, we're going to divide the difference of the two values, and then we are going to divide it by the standard error. So that's going to be our test statistic. So the test statistic is going this unbiased predictor is going to be the difference between the two samples. So the proportion of the two samples. So so we know that so this is the observed difference, and this is the hypothesized difference. So the observed difference is what we do in our experiment. So I want to know what is the proportion of women at Lehman College. So I am going to have a number. So and I'm going to measure it against another sample proportion. So the observed is going to be based on our samples. So and the hypothesized difference is going to be 0. We are hypothesizing that is 0. So the observed difference is going to be divided by the standard error. So and remember that the P bar is going to be given by this formula, which is a little bit long, right? So so we find these values, and then we are going to make sure that these values are at least R5, right? So so once again, we look at the case, we translate the verbal into a mathematical claim. So we want to know the level of significance. So with the level of significance, because we are using a seed test, we can find the critical values. So remember, with the level of significance, we're going to find a critical value. So then with this, we're going to specify the rejection regions. So remember, based on our hypothesis, we have to determine whether it's a left tail test, right tail test, or two tail test, right? So we find the weighted estimates, blah, 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 make sure that everything is fine. So we perform all these computations. Remember, the observed difference divided by the standard error, which is a big thing. So if C is in the rejection region, we reject H naught, otherwise fail to reject H naught, okay? So it seems like a lot of work, and indeed it's a lot of work, but I'm gonna tell you that what I found in the internet is very simple to follow. So so it doesn't mean that anybody's cheating. We are using resources that are there. I don't see why we shouldn't use it. And we are using it for a very simple purpose, which is solve a problem. So in this case, what I want to say here, so this is the case, this is the Excel file. I think you should be able to open it. So we have been working on this. As you can see, the green are formulas. And those are formulas that are a little bit, like for example, this is the formula for the p hat, or it's called p hat, but actually is the p bar. So this p hat is going to be this value. So once we find, or the program finds p hat, q hat is going to be 1 minus p hat. So we have the standard error, we have the c value, we have the p value. So that's very important. The p-value is gonna, just by looking at the p-value, if the p-value is less than the level of significance, we reject H naught. So, and this is more beautiful because it gives you different stars. So this star, for example, if this cell gives you 3 stars, it means that the value, the p-value is less than 1%, which is super good because it's less than 1% level of significance. If this cell gives you 2 stars, means that the p-value is less than alpha equal to 5%. And if it has only one star, means that the p is significant is lower than the 10%, right? So you don't have to do many things. Even more here, this cell is going to tell you, well, don't worry, this is significant or this is not significant. So that's very nice. Let's erase this number. So as we can see, all we have to do is to put the proportions, to put the sample sizes, and to include the alpha. So we are going to get the C value, which is my test statistic. And then we're going to get the critical value. We are going to compare the C with the critical, and we are going to make a decision. So in this case, this is very interesting and very nice because we have an so alpha. So remember, we are doing the C test. So in this C test, we don't have like the T test where we can indicate Excel to compute the two tail. Here, if there is one tail, so we put the number, and if it's right, we use the positive. If it's a left tail test, we use the left. If it's a left tail test, we use the negative number. If it's a two tail test, we're gonna divide alpha by 2. So if I have a 10% level of significance and it's a right tail test, I'm gonna put here 0.10, and I'm gonna use this number as a positive number if it's a right tail test. If this is a 10% and it's a left tail test, I'm gonna keep this number as negative. And if this is a two tail test and the significance is 10%, I'm gonna use 5%, right? So that's what we have been doing in many cases. So we have to look at the values in our Excel files and make sure that we are doing the right thing. So technology can do many things for us. We just have to know how to use it, okay? So, so in this case, we're gonna make this very simple. So we have a case. So in a study, 150 randomly selected occupants in passenger cars. So I can even write here passengers versus pickup, right? So I just can personalize it more. So remember, this is 2 samples. We are using 2 different proportions. So 86% of the occupants in the passenger cars. So here we have a 0.86. And here in the second one, and 74 occupants in the pickup truck wear seatbelts. So 0.74. So the question is, at the 10%, at alpha 10%, can you claim that the proportion of occupants who wear seatbelts is the same for passengers, cars, and pickup trucks? So that can be a very good question, because let's say that you are a policymaker and you want to enforce these laws. So you take a sample, measure the proportion, and make sure that your claim is correct. So can you reject the claim that the proportion of the occupants who wear seat belts is the same for passengers and pickup cars? So of course, if I have my hypothesis here, so my H sub 0 is going to be the proportion 1 is equal to the proportion 2. Remember, this is the parameter. And then my alternative is going to be that they are different, right? So very clearly, we have a two-tailed test, and we need to do this two-tailed test. So whatever we are going to find is going to be expressed in a two-tailed test, right? Okay. So we are going to have two rejection regions, because this is a two-tailed test, right? So what do we need here is also the sample size. So in this case, if I type 150 and then 200, so as you can see, so we have all the results here. So let me erase these numbers. So look at this. So let me move this. So if I put the sample size here was how much? 150 and then 200, right? So look at the, so by including these numbers, I already computed P hat and Q hat based on 1. Now I'm gonna use the second, which is 200. So you can see that we're gonna find the standard error. We're gonna find the C value, the P value, which is very important. The significance, I told you, 3 stars, 2 stars, 1 star is gonna tell you this value is significant at 1%, 5%, or 10%. So, and here you're gonna see a text that says whether or not it's significant. That is very beautiful, because this little program is helping you to determine many things without, well, I mean, of course, it's giving you the results. Now you have to make the interpretation, right? So here, proportions are significantly different at the 99%. So that means that, so we have 3 stars here, right? So we have 3 stars here, meaning that this is significant at the 1% level. So that is beautiful, because your type 1 error is only 1%. So so the probability of being wrong is going to be only 1%. So so in this case, this gives you everything. So far we have the C value. So the C value is 2.74, 2.73. So I need to know the alpha. So in this case, the alpha is the 10%, but because it's a two-tailed test, I'm going to use a 0.05. So my C value, my critical value here, let me write this down. I'll probably make it. So maybe not too much. So in this case, my alpha, which is the 5%, helps me find the critical values. So my critical values is going to be 1.645 and plus 1.645. So remember, we have a 10% level of significance. We have to include only 5% because it's a two-tailed test. So so my C score is 2.73. So very likely it's going to be somewhere in here. is the 2.734. So I need to find, I need to do this because the results are here. I need to make sense. So I'm sure that my p-value is less than 1%, is 0.007. So is lower than the 1%. So let's say that my alpha is 10%, of course, is significant. So it can, even if I set an alpha to the 1%, is going to be significant, right? So so that's how my results are described. So so I can look at the p-value, and just looking at the p-value based on all these computations, I can determine that this is significant, right? So I also have these 3 stars, and I have these results. So let me show you something. I'm working on a project on COVID. Let me see. Hold on. So that's how some of the so when you are using software, I mean, all these results, are super easy to compute. All you need to know is to make the proper call. For example, this is my colleague who is doing this work. So he used R. So this is the regression, of course. We are not describing the regression, but as you can see here, so we have the stars. So I probably don't see these numbers. I just go to the stars. I say, oh wow, all these results are significant. Now I am looking at the value of the estimate, and I am looking at the p-value. So that leads me to believe, like for example, in this case, this is significant at the 10%. This is significant at 1%. So so that means that if I move this decimal, I have to move this decimal point. Remember, the E means scientific notation. So I have to move the decimal point 9 positions to the left. So this number is going to be very close to 0. So that's how reports are made. So we are doing this basically by hand, and not necessarily by hand. So we are using technology, but that's what you get. So in this case, we have to do the tough work that so we need to do. So in this case, so the claim is that reject the claim that the proportion of occupants is the same. So the claim is the so this is the claim. Let me just use a C. It's a claim. So because I am rejecting H naught, so I don't have enough evidence to support the claim. So in this case, the claim happens to be H naught. So I don't have enough evidence. So in this case, as you can see, all these values, so we have the values that we included, sample sizes. This is my critical values. Remember, we use the alpha, and we use the here the normal distribution inverse to find to convert this area under the curve in a two-tailed test. Remember, it was 10% alpha. Now, so we have half of alpha. So my critical value is 1.645, negative and positive. So we have the critical value. So we have the computations here, as you can see. Ay, Dios mío, hold on. So here, let me highlight some of the values. So in this case, well, in this case, as you can see, 17.7914. So we have here the p bar is not the p hat, is the p bar. So this is the weighted average of the populations. So we have the p-bar here. So we have the q-hat, so automatically found. So of course, in this case, 200 subjects is almost very sure that we are going to have at least 5% on each arm. So we didn't do this. We can set up this case for making sure that we can compute. This is the sample size. So and this is the different proportions. Let me see where these numbers are coming from. So there might be some p-bar 200, q-bar. Okay. So we are using these numbers. I think they are inverse, but it's fine. I don't know this number where it's coming from. Oh, this one. But regardless of this, so we have a result. So this is the sample size one. This is the second sample. What is 65? I think this can be mistaken because those are the values. So this is the value that, but regardless, I think there might be a mistake here. So so this is good, but and probably is inverse. So we have to review this. I think it's not accurate. So so you have to follow the formula, and so based on the formula, so we can say that multiplying the sample size times the weighted average of the probability of success, the probability of failure, those numbers have to be greater than 5. So when we find these numbers, we can just multiply it by the different values just to make sure that those values are greater than 5. So and those numbers are wrong because this is sample number 2. So sample number 2 is 200, but sample number 1 is 150. So this is definitely wrong. So please scratch this from your work because this is wrong. So the values that we are using here might be more accurate. So so here they are using the sample size times the p-bar, and this is the sample size 1 times q-bar. So so I think the formula is accurate, but the values are not. So here we can do the same. We can say that here multiply the sample times the p-hat, and then this is hold on. Move it over here. So then this is n1 times p-bar, right? Or p-hat in this case. So this is going to be the value. So this is going to be n1 times q-hat, right? So that's going to be equal to 150 times this number, right? Hold on. So I'm going to use equal this number times the q-hat, right? So we are going to do the same for the second. So as we can see, this number is clearly greater than 5. So we are checking that. So now we have sample size 2 multiplied by p-hat. And then we have sample size 2 times q-hat. So probably we should keep this because so in case that you have a different numbers here, so we can use this. I think that's the proper thing to do. So we are going to do the sample size 2 times p hat and the sample size 2 times q hat, right? So in these two cases, these numbers have to be equal to, this is 150 and that should be 200. And I guess that is the case. So let me just make sure that this is true. This is 150 and this should be 200. Okay, yeah. So we are fine. So we have this, that wasn't that difficult to do. So we have all the information. So please disregard this. I think is completely wrong. And I didn't realize until now. So so this is completely wrong. Ignore it. So use this. So every time you change the proportion, for example, if you have 200 here, so then that modifies very easily, right? So we had here 150, right? So let's look at the second case. So the second case is very similar. I really want to. So and the beauty of these Excel files is that you erase your results, you can do this again. So whenever you are changing these numbers, you are going to find the values very, very easily. So let's look at the second. So the second is a little bit fun because we don't have the proportions. And that's what happened more in real life in experiments. You are given data, and that data is going to be, so you have to work more on the data. So the second one, so this is what we got here. So well, I think I erased it, but that was our 273 is our C score. Look at how many steps to find this value. So this is the solution. So at the 10% level of significance, there is enough evidence to reject the claim that the proportion of occupants wear seatbelts in the same for passengers, cars, and pickups. So so once again, that was the claim. So yeah, so we have enough evidence to reject the claim. So probably I said something different, but I think this is right. So we are rejecting the H naught, and the H naught happens to be the claim. So we have enough evidence to reject the claim. I think that's very, very, very good to say. So so that is the first case. The second case, as I mentioned before, is a little bit more realistic, because in many cases you have a number, you are running an experiment, you have your patients, and you know how many of them are sick, how many of them are not. So in this case, we can use still this, because we can convert this number into proportions. Okay, so so let me do the following. So a medical research team conducted a study to test the effects of a cholesterol reducing medication. So at the end of the study, the researchers found that of the 4,700 randomly selected subjects, so as you can see, that probably is a clinical trial. The number of people engaged in this are big. So so it might be like, for example, I was talking a little bit about clinical trials, and there are 3 different phases. The first phase goes in a very small sample. So they are trying to look at the toxicity of the medication. So they use healthy people, they give them very small doses of the medication, and if they don't have any side effect, so they move on in the second phase to test the efficiency of the medication. So they use sick people and they give them a very controlled substance, so very measured substance. And then if people respond well, they take a bigger step and they make a third phase. So in the third phase, that they use a very big sample and they want to make sure that things are fine. So probably this is kind of like a second phase, because the number is large enough For example, if you see the COVID vaccines, they are using thousands and thousands of people. So that's the case. So in this case, we have a sample size in the first arm that is 4,700. So out of them, 301 died. So, but 301 is not a proportion. So becomes a proportion when I said 301 divided by 4,700, right? So that is my proportion. Only 6% of the people taking the pill died. So I want to know if in another arm. So so in this case, we have an arm that are using the medication. The second one is using the placebo. So the one in the medication, we have 4,700, and the one in the placebo group, we have only 4,300. So, and we have some people who died. So those numbers, as we can see, the samples are different. So, and the number of people who died are also going to be different. So what I'm going to do is I'm going to test these samples. So in this case, I will change the notation. Those are medication, and this is the people in the placebo group. So remember, the placebo means these people are taking the medication, these ones are taking the sugar pill. So in this case, I have 301 who died out of the 4,300. So here we have a 6.4%. Here we have a 6%. So let me make this even. So probably I'm gonna.
Professor?
Yes, young man.
Shouldn't it be 357 over 4,300 for the placebo?
Oh, sorry. That is absolutely right. That is absolutely right. Sorry. So I was misreading. Yes, out of the 4,300. Thank you very much. I was just testing, guys, if you are still awake. Thank you for correcting me. 357. Thank you very much for correcting me. So we have very good. So in the medication group, 6.4% of the people died. In the placebo group, 8.3% died. So I want to know how different these proportions are. So as we can see, I did the p hat, the q hat. Once I computed the p hat, q hat, I was able to find the my conditions. So I'm going to put here with big letters conditions. So those conditions are met, because if I multiply n1 times p hat or p bar, so I have an arm that is greater than 5. So let me just make this less zeros. These less zeros. So so I have a number that is greater than 5. So that is the number that I should aim for. So let me use another color, some little blue. So this is the test that I need to perform. So my tests are fine, so I can proceed to read the results. So in this case, because these numbers are greater than 5, so I computed the standard error, and I have a p-value, a c-value of -355. So once again, do I care for that? Probably not, because my p-value is extremely low. It's extremely low. So so in this case, I have 3 stars. So if I am setting here a 1%, so with this, my p is less than 1%. So am I happy? I am very happy, because my p-value compared to the level of significance is smaller. So I'm very happy, because my so in this case, my claim that the people who are, so here, so what is the case? So at the 1% level of significance, can you conclude that the death rate due to heart disease is lower for those who took the medication than those who took the placebo? So people who don't know statistics too much, they say people dying and say, well, people die, so why should I take the medication? But statistically speaking, so in this case, my proportion, let me make this clear. So the proportion here, no, I just want to, I don't want to raise everything. But it seems that I have to raise everything. Well, so to make the, oh, here, that is not what I want to see. So this is gonna be, the death rate is less than, is less in the medication group that in the placebo group. So this is equal or greater than. So let me just do this, okay? So so the claim happens to be the alternative. So in this case, what should I do? So I have a p-value that is lower than my alpha. So of course I'm happy because I am able to reject H naught. So my alternative happens to be the claim. So I can support that my values are fine. So let me erase this. Let me erase this because my new critical value here, I haven't modified the critical value. So so my critical value here, so here is a left tail test. Whatever I'm doing is a left tail test. So it's a 1% level of significance. So I need to modify this. This is 0.01 and it's a left tail test. So my critical value here is gonna be minus 2.326. My C value is minus 3455. So it's gonna be somewhere in here, right? 3.45. So negative. So clearly using the the p-value, I can make the call. I can see the significance here. But now I am making this more formal because it's not about finding the values. You have to conceptualize the idea, right? So in this case, you are sure that your C score, the C statistic that you just computed, falls inside the rejection region. So this is a 1% level of significance in a left tail test, okay? So I will have enough evidence to reject the H naught. So in this case, as we can see, 47, 43. So this is more correct. So please make sure that we are looking at these values. So so this is the p hat, the q hat, yes. So this, sorry, this is the p hat, q hat. So as we can see here, so the previous one was wrong. This is correct. So we have the values. So so we have the test statistic that we just computed, 3.46. So this is the C score based on my data. So remember, this is the observed difference. This is the variation. So I get my C score, which is 345, exactly the same I measured. So I have my my critical value of minus 233, which is based on my alpha at a left tail test. So with this, I am able to reject. So once again, the rejection part here, this is very clear. My p-value is extremely low. So it's less than 1%. So if this is at the 1%, so even I can call for a 0.001, for example. So let me make this. So what if I do, this is the 1%. What if I want the 0.1%? So not the 1%, but the 0.1%. So, and I will be able to still make it work. So my critical value is going to be 309, and still my my level of significance. So my CS score still falls within the rejection region. So this is a very small level of significance. So if somebody tells me that Lipitor or whatever the cholesterol pill is there, so it works. It works because the death rate, which is a very important measurement of success for medications, especially this kind of conditions, high cholesterol causes um, premature death. So I will be able to say that is significant. So here at the 1%, I have a very good significance according to this. So once again, if I am the person in the pharmaceutical company, I will probably use the 0.001. So I will do it at the 0.1%. So in this case, my results are very significant. So I will be very happy to do that. So in this case, at the 1% level of significance, because we are rejecting the H naught, so we have enough evidence to support that the death rate due to the heart disease is lower for those who took the medication than for those who took the placebo. So so these cases, and I hope you guys can use this and not only use it but go beyond that. So so these formulas, I mean, they can be easily done. Some of them require a little bit more of work. So so I invite you guys to look at what happens in each case, right? So so here, for example, we have something that we didn't cover in class, but if I want to know the p-value based on the C score, that's how these guys found it. So we might have another way to do it, but in this case, they found these values. So is there any question so far? Is there any question so far? No? Yes? Okay, so you guys have this. Okay, good. So I have been thinking about the next steps, and I know that by this point, everybody is exhausted. Everybody, including myself. So and not because I mean, I am kind of working a little bit hard. So what I want to say is the following. So and I hope you guys agree. So so we covered so far this is the last module. So we covered this hypothesis testing with 2 samples. So where are you guys? I don't see anybody who is here. So so we are covering hypothesis testing for 2 samples. So I'm gonna continue next week doing the chi-square distribution, but I can tell you that just because I am in a very good mood today. So I'm gonna go through the chi-square distribution. So you don't have, once again, you don't have to do the chi-square in sapling, and you do not have to do the test in this module. All I am gonna, so you get 5 points here, and you get 5 points here. So the only one that you have to do is this and Excel, okay? So I hope it helps. I think many people might need some time. I know that papers are coming, papers, exams, and many things, family issues are coming up in the next couple of weeks. We're getting close to Christmas. So, and I hope it helps. I hope it helps. And I also hope that you guys show up next week and continue with the chi-square. It's a very good test that you need to know. I'm going to repeat myself. You don't have to, you have to do hypothesis testing with 2 samples here in Sapling. You don't have to do the chi-square. I'm going to teach it, but you don't have to do the problems, and you do not have to do the test. So the test and chapter 11 is kind of like a Christmas gift, and all you have to do is to do the chapter corresponding to hypothesis test. So here is like 10 points that you are going to get. I just need the Excel file. Okay, so you give me the Excel file. So you give me the Excel file and you complete hypothesis testing with 2 samples, you are going to get the full points. This is 10, 15, 20 points. Okay, so is there any question?
Professor?
Yes.
I'm just asking, if I try, I still get the 10? Or
of course,
yeah.
Of course.
Okay,
that can be also an incentive if you do.
Yeah, just to try. So if I have
okay,
time, yeah.
Sure. I mean,
okay.
I'm gonna go through the whole chapter, and it's gonna be. I mean, yeah, no, of course. I will be happy. If you try. That might be extra credit for those who.
No, I mean, if I get, for example, from 10, I get 7 points, I still get 10, or?
Yeah, I mean,
okay.
Whatever you get here, like for example, if you get the 5 points.
For the optional.
Yeah, so if you get, for example, here, few points, I'm gonna give you the full point. So it's more like practicing for you.
Yeah, it's clear. Yeah. Thank you.
Okay. Yeah, of course. So it might be nice. It might be nice, even if you, if somebody does it, I will use it as
I'm thinking for econometrics for next semester, and just I want to try. So it's similar, right? The econometrics with this.
Yeah. Like well, econometrics is more like what I'm doing here.
Yeah.
So you are gonna start using bigger databases. You are gonna build equations that. So those are the estimates.
Is this so hard class, Professor?
Well, it's hard. I don't think it's hard. I think it's a lot of work. I mean, it's not a lot of work. It's more like thinking, because in the next semester you are going to be using. I mentioned before, I guess Professor Papa Nicolaus, he uses Stara. So this program. So when you use this program, you obtain outputs like this. For example, that you are not computing anything. So all that you learned in this class, doing everything in Excel, I hope you get the idea what it means. Like, for example, in this case, let me show you. So next time we are going to be using the chi-square test. And the chi-square test is for independency. So we are going to do it by hand. But here you get the score, and you get the probability, which is, I mean, all the results are there. The only thing that you need to know is, why do I need this test? So so the test for independency and some things, you don't have to compute it. The program does it for you, but you need to know how to make an interpretation of those. So it's more like thinking, using the right tool. There is always one tool for something. Like, for example, if you look here, so we are using, well, it's different. This is a regression based on some assumptions. This is the same regression based on something different. So we are comparing results, and so my point is, econometrics is more about thinking what you need to do with the data. What is the best tool that you are going to use to make an interpretation of the data? That's about what you are going to do. Is difficult because there are so many elements, so many things that change every, like, it's like what we are doing here. So we have the confidence interval. So for example, in this case, as you can see, so we are finding the estimates and the standard errors, right? Here we have what is called the odd ratios, and that is the confidence interval. So for example, you need to know what that means. So when you are using an estimate of this, or you are using an odd ratio, reporting estimates, you report the standard error, reporting odd ratios. In this case, you have to do the confidence interval. Is that difficult? Probably yes, because you have to kind of like know exactly what you are doing. But it's not, I mean, it's very technical, very technical. It's a beautiful class. It's a beautiful class. So if you take it, please use your time wisely, because it's a beautiful class.
Yeah, sure. Thank you, Professor.
So yeah. So you just have to do chapter 10. You don't do chapter 11. You don't do the test, and you send me your Excel file. So and the Excel file for the second case is going to be even more. It's going to be easier, because all we have to do is to just fill out these cells, and we're going to solve it. So we have more categories. We have to add more. And I will show you how we can do it. So but it's very easy, very simple. That all this work can be done using technology, and it's very easy. The only thing, once again, we need to know is why we need this stupid formula. So we need it because we want to prove, and we want to test that our results have the significance that is required to make sure that my results are valuable. So so that's what we are doing now. That's what you are going to keep doing next time. So next time when you are building a case and you have to report your results using a confidence interval, you know what that means. So you know that you are using a sample, and you are using a confidence interval that tells you that at that particular level of confidence, you can state that the mu, or the real parameter, falls in that segment according to the level of confidence. So so that's basically it. So next class we're going to continue with the chi-square, and then we are going to be done. Okay. So any other question?
Professor, I just want to make sure I heard you correctly. So for our last assignments, is the assignments or sampling learning, the 3 assignments, and then the Excel assignment is the chi, for Excel.
Oh, for Excel is the 2. Very good question. So in Excel we are going to do the chi-square, which is already uploaded. So and also we are going to do, so what we did just today, the hypothesis test with 2Sample, which is basically very simple. I mean, all I want you to do, guys, is just to try these ideas in Excel to see how easy. And I don't want to take the easy road. My goal is that you are wise in the sense that you have the results, but you need to rationalize what are the how to interpret the data. So in this case, so in some cases I am even highlighting what is important. So that's the idea in Excel. So is to make your life easy and to take advantage of technology. And in many cases, technology does everything. So I'm more in favor to use these values to see the significance or the importance of the things that we need to prove. So so that's the idea. But going back to your question, yes, I want you to explore these things to come up with the same results as I did, and then just to try it and submit hypothesis testing with 2 samples and the chi-square. So that's gonna be it. Okay.
All right. So we should attach everything to one document, or
I think I have seen that you can enter two different, for example, let me see. So here we have module 5. So let me include, that's a very good question, a very assignment. This is gonna be Excel 5. So you include your thing here, and this is 5 points, right? So you have a Dropbox here. I think you can include the two. So browse your computer. I'm going to include one, and then I think I can include two. Hold on. Browse my computer. Have distribution. Yeah, I can upload two files. So you can upload the two in the same file. Okay.
All right, thank you. And then sapling learning, those are the last assignments for the semester.
For sapling learning, you just have to do number 10.
Oh, so we don't have to do chapter 11 and test 5?
No, you don't have to do chapter 11. You don't have to do test 5.
Okay, got you.
I'm giving a 10 points gift to the class.
Oh, wow.
For being so efficient. Yeah, I mean, I'm very happy because many of you guys are doing an outstanding job. So I'm very happy to do that. So, and also to help some students who might need this help, so they can focus their attention on chapter 10 and probably the Excel file, so they don't have to do these two things. So I hope it helps. I hope it helps, and if there are no more questions, let me stop the recording. I think I'm saying too much in public.